Okay, this is Jeff Coles. In this unit, we're looking at alternative or additional characterizations of a solution of a linear system of ordinary differential equations. Linear system, again, can be written as this: the rate of change of x with respect to time equals ax plus by, and y prime equals cx plus dy. This would be a system of two linear equations, two unknowns that you're trying to solve for x of t being the independent variable, and y of t. Previous unit, we guessed the solution, where we wrote the system of equations in the form z primed equals az, where z is a vector and a is a matrix. And we guessed the solution of the form z equals c times v e to the lambda t. And we found that this would satisfy that differential equation, provided lambda was an eigenvalue of A and V was the associated eigenvector. And thus we wrote the final general solution: z equals C1 V1 e to the lambda 1t plus C2 V2 e to the lambda 2t. For a system of two equations, because we have two eigenvalues and associated eigenvectors, and these constants can be determined by the initial conditions. The key parts of the transient of the solution came from the time dependency, which is wrapped up in these exponential terms, where the lambdas are the eigenvalues of A. We looked at two cases, one with real negative eigenvalues, and again, the system of linear equations has one critical point, that is at the origin, when x is 0 and y is 0. When the lambdas were real and negative, these exponentials tend to decay towards 0. And thus, whatever the solution started from will be drawn towards our critical point. We also looked at the case where the eigenvalues were real and positive. In that case, these time-dependent terms will grow. If they start at the origin, they will grow away from the origin. Two different characteristics. One was the lambdas were real and less than 0, both of them. The other, the lambdas were real and greater than 0. This one was the nodal sink. It is stable, a stable system. This is a nodal source. It is an unstable system. Now, we've studied already, when looking carefully at the predator-prey equations, we saw the system had a point here where we had coexistence of the two species as a critical point, and we evaluated the solution near there using null Kleins. We found that the solution essentially in phase space did something like this. So we saw an oscillatory solution when we plotted x and y versus time. We saw that they were essentially oscillating. They were doing some kind of oscillatory behavior, about 90 degrees out of phase, which matched the original observations that led to the development of these equations. And so far, by looking at either positive real eigenvalues or negative real eigenvalues, the nature of this solution around the critical point, the origin, doesn't really match. There's no oscillatory behavior associated with this. It's simply decay or growth. And that's because we're missing other types of eigenvalues. It's always going to be controlled by the eigenvalue, but we've been ignoring other critical types. So how do we get these periodic solutions? How do we add periodic or oscillatory components to the solutions? Well, it comes from having complex eigenvalues. Now, in general, a complex number can be written in the form lambda, we'll write as an eigenvalue, alpha plus I beta. Complex number has a real part. It has an imaginary part. And I, which we defined in the previous unit, is the square root of minus 1. By definition, that is the imaginary number. So a general complex number can be written by this. If it's purely real, beta will be 0. If it is purely imaginary, alpha will be 0. Now, how does this lead to having oscillatory behavior? Remember again, our general solution looks like this. Z of t, z which is our vector, state vector, equals C1 V1 e to the lambda 1t plus C2 V2 e to the lambda 2t. For a complex number, lambda equals alpha plus I beta, we can use Euler's formula to see what happens when we put this in the exponent. Remember, these are the transient terms. These are the important ones. What does e to the lambda t look like if lambda is complex? Well, it looks like e to the alpha plus I beta times t. If you're comfortable with exponents, exponential numbers in general, this is equal to e to the alpha, e to the I beta t. Now this thing here, this thing right here is going to be, oops, excuse me, I missed a t here. E to the alpha t, e to the I beta t. This first part here, let me clean this up. This first part is e raised to a real exponent times time. And the second part, e raised to a complex exponent, a complex part times time. Now this thing can be expanded using what's called Euler's formula. Euler's formula states that e to the I theta, where theta is some number, is equal to cos theta plus I sine theta. Provided theta here is real, so I theta is a purely complex number. This is Euler's, one of Euler's many doings, but this is known as Euler's formula. And it relates complex exponentials with harmonic functions. This is a fairly commonly evoked formula. And this tells us that if we have a complex, and generally speaking complex, eigenvalue, we can write it as e to the lambda t equals the real part times the imaginary part. E to the I beta t, replace theta here with beta t, we get cos beta t plus I sine beta t. So the argument of the cosine and sine is beta t. So the imaginary part makes it into these cosines and sines. The real part of the eigenvalue is in the exponential envelope right here. We call that an envelope, and I'll show you why in a second. Now we plug this general into our general solution. Now keep in mind the eigenvectors are generally complex as well. So what happens is you get lots of cancellations. There is an I here, but because this is being multiplied inevitably by a complex eigenvector, the complex parts start to cancel out. And the result is something that looks essentially like this. Now I won't go through the details because it's quite time consuming. But the key thing is that our general solution ends up looking like this. E to the alpha t cos beta t can be written this way, plus k2 e to the alpha t times sine beta t, and y of t equals k3 e to the alpha t sine beta t plus k4 e to the alpha t cos beta t. Now, why do we only have alpha? Remember, we have two eigenvalues. When you have a system of two equations and the eigenvalues are in general complex, the eigenvalues will be what we call complex conjugates of each other. So you'll have a lambda 1 that will look like alpha plus I beta, and you'll have a lambda 2 that looks like alpha minus I beta. These are known as complex conjugates. The real part is the same. The imaginary part is one is a negative of the other. This is the way they come in if you have complex eigenvalues, and actually the eigenvectors will also have this look to them. So that allows us to write the system like this. This is what the system ends up looking like if beta is non-zero, if you have an imaginary part. So you have these kind of functions, let's just draw one generally speaking, that look like this. They have an exponential function, which we've seen. That's where the time dependency was in our previous examples. And now there's some kind of harmonic. Let's just use a cosine. What does this look like? Well, this part right here, this function, is just repeating and repeating and repeating, right? And the period is 2 pi over beta in time between two peaks. But then you're multiplying it by this thing, right? Where alpha is real. So if alpha is greater than 0, well, this would be the case if alpha equals 0, right? E to the alpha t would be 1. You just have the cosine part. So if it's purely imaginary, you just have pure oscillation. If alpha is greater than 0, then this thing in front is going to be growing and growing and growing. Think of it like an amplitude, but an amplitude that depends on time for our harmonic function. So we have something multiplying our oscillatory component, and that something is getting bigger and bigger. And so our oscillations will grow in amplitude. The period will not change, but the amplitude will change. Oops. If our alpha is less than 0, oops, then you have a decay term here. If alpha is less than 0, if eta then is some negative number times time, it will decay. So you have a decaying amplitude, and in that case, it's going to just damp out. It's a damped oscillation. So you have undamped oscillation, unstable oscillation or growing, and you have a damped oscillation. In all these cases, the period is 2 pi over beta, unchanged. What changes is the amplitude. The distance from the mean value of the function to the peak of the function is going to change with time. If we connect the peaks with the function, and the troughs, that function forms an envelope. The oscillations live inside an envelope that's converging from the positive side and the negative side. That envelope is the exponential function. It's an exponential decay. In this case, the envelope, it's not very well drawn, but the envelope is growing, and this is exponential growth. So again, now we think about our eigenvalues, lambda, which can be generally written in complex form alpha plus I beta. And alpha still controls growth and decay, if it's there. It's the real part. If it's real and positive, it will grow. If it's real and negative, it will decay. And beta controls the oscillation. In our previous examples where we worked through numbers, we had purely real eigenvalues. Beta was 0. There was no oscillation. If beta is non-zero, you have some oscillation. So let's look through a problem with real numbers again. We have new numbers compared to the previous case. Negative x minus 3y and y prime equals 3x minus y, which we can write as z equals a z. So a is going to be minus 1, sorry about that, minus 1, minus 3, and 3 minus 1 times z, and we compute the eigenvalues of this, and we'll find lambda 1 equals minus 1 plus 3i, and lambda 2 is the complex conjugate, minus 1 minus 3i. So alpha equals minus 1, and beta equals 3. The sign of beta does not matter, the imaginary part, just whether it exists or not. Imaginary part, real part. The real part is negative. That implies that the system is going to decay. The imaginary part is non-zero. The system has oscillatory behavior. The general plot of the solution, if we solve for initial conditions of x at t equals 0 equal 1 and y at t equals 0 equal minus 1. That's supposed to be minus 1. Here's the origin. This is time. So x is starting here. It sort of oscillates like this. And y is starting at minus 1. And it oscillates like this. So in both cases you have damped oscillations. They're damped. We know they're damped because the real part is non-zero and it's less than 0, it's negative. And we have oscillations because we have an imaginary component. In phase space, something like this would look like this. Again, here's the critical point of our linear system. It's the origin. We started at 1 comma minus 1. That was our initial condition. And it will proceed to oscillate. Oscillating functions imply spirals in phase space. In this case, spiraling into our critical point as it decays towards 0, 0. This type of linear system is known as a spiral sink. Remember, we already looked at the nodal sink, which had no oscillatory component. It is stable. Solutions tend towards the critical point when perturbed from the critical point. What about purely imaginary eigenvalues? For example, x primed equals 4x plus 2y, and y prime equals negative 10x minus 4y. This has eigenvalues. Lambda 1 equals 2i, lambda 2 equals minus 2i. They're still complex conjugates because the imaginary part, one is a negative of the other, but there is no real part. It's a purely imaginary solution, which means there's no exponential decay, meaning a solution will just simply oscillate and continue to oscillate. Maybe this is x of t, maybe y of t has a larger amplitude. In this linear system, both of them will have the same period. Again, the period is 2 pi over beta. Beta in this case is 2, so we have 2 pi over 2. Our period t is going to be pi. The distance in time between two successive crests or troughs of either system is going to be pi in this case. What does it look like in phase space? Here's the origin. They're just oscillating around and around and around and around and around, right? Forming closed loops. It's not well drawn. It forms a closed loop. If I start here, it forms a closed loop. Back to the point. There's no exponential decay or growth. So at some point after one period of time, pi of time in this case, it comes back to the exact same point it was at before. This is phase space, x versus y. This is known as a neutral center. We have seen this already when looking at the predator-prey equations, a neutral center. Now there are others. So we've looked at the prior unit, we looked at the nodal sink and nodal source. Here we've looked at spiral sink. Spiral source is when we have our eigenvalues. Lambda 1 equals alpha plus I beta, and lambda 2 equals alpha minus I beta, again complex conjugates with alpha greater than 0. In that case, our phase space is going to look like this. Here's our critical point, and it is going to spiral out. Our directional vectors are facing out of the critical point. Any perturbation from the critical point, it will spiral out in space, and the resulting, so again, this is the phase plane, x versus y. This is the time frame, x and y, here on the y-axis. And we have growth. We have oscillation of a growing amplitude. The y will do something similar. This is a spiral source. It is unstable. So we looked at spiral source, spiral sink, nodal source, nodal sink, neutral center. And there's one more that we didn't look at. It's a case of two real eigenvalues. Lambda 1 is real, and greater than 0, and lambda 2 is real, purely real, but less than 0. So we looked at both positive, both negative, but what if one's positive and the other's negative? This is known as a saddle point. Again, we visited this already with the predator-prey equation. Saddle point is such that you have in phase space, there will be one line somewhere. Along that line, the solution is stable. It's attracted to the origin. Everywhere else, it is unstable. So it's considered unstable, even though there is a line along which it's stable. So there's a theoretical initial condition, infinite number of initial conditions along this line that will attract towards the origin. Every other initial condition are unstable because we have to consider perturbations of any kind. This is an unstable solution. Your lecture contains a summary, lecture notes contain a summary of all the different types. You have a nodal source, which is unstable, and that has two real the eigenvalues are purely real and positive. You have a saddle point, which is unstable. The eigenvalues are purely real, one is positive, one is negative. You have a nodal sink, which is stable. The eigenvalues are purely real and negative. You have a spiral source, which is unstable. You have complex eigenvalues, which have a non-zero imaginary part. The real parts of the eigenvalue, the real part of the eigenvalue is positive. You have a spiral sink, which is stable. It is made from a system with complex eigenvalues. The imaginary part is non-zero. The real part is negative. It is stable. And finally, you have the center, which is purely imaginary eigenvalues. The real parts are 0, and that is neutrally stable. Now, coming back to our evaluation of the predator-prey equations, we evaluated the predator-prey equations at the two critical points. So let's have a look at those equations again. We have x prime equals ax minus bxy. That's nonlinear. Y prime negative cy plus dxy. We linearize these, and producing the Jacobian that looked like this. A minus by negative bx dy negative c plus dx. That was from the lecture on linearizing a nonlinear set of ordinary differential equations. First critical point was the origin. X naught, y naught equals 0, 0 satisfies x prime, y prime equals 0. It is a critical point or equilibrium point. And the resulting linear system there was u prime v prime equals, plug that into this Jacobian here, we get a 0, 0 minus c times uv. Now, linear system has two eigenvalues. It's a diagonal matrix A. The eigenvalues are the elements of the diagonal. One's positive, one's negative, both real. This is a saddle point. It is unstable. The other critical point was, let me go back to the system, pull x out of here. When y equals a over b, when x equals c over d, you get a critical point. So it looks like this: x naught y naught equals c over d, comma a over b. Plug that into our Jacobian, and we get a new set of linear equations valid around this point here, which look like this: 0 minus bc over d, a d over b, 0. The eigenvalues of that are plus or minus I, A, C. They are purely imaginary. This is a neutral center. Now, going back to our original discussion in class about the solution of the predator-prey equations, make this a little bit bigger if I can here. You have two critical points here and here. This is prey. This is predators. If there are no predators and we introduce some prey, the system grows unbounded. If there are no prey and we introduce some predators, they die out back to the origin. And we use nullclines. There are two nullclines that look like this, and we were able to surmise that the system essentially produced oscillations around, rotational oscillations around this interior coexistence critical point. And so we saw already the characteristics of this equation. And the directional space looks something like this, that we have two critical points, one with purely imaginary eigenvalues. This one here is a neutral center, or sometimes called a center. And this one here is a saddle point. Has one positive real eigenvalue, one negative real eigenvalue. That magical axis along which the system is stable happens to be x equals 0. It's the y-axis. All the other perturbations away from this origin are going to lead to something else, away from this critical point. So essentially, by knowing what the eigenvalues are, we see that we can characterize any linear system simply by looking at the eigenvalues. For nonlinear systems, we can examine what's going on at critical points by linearizing around the critical points and then evaluating the eigenvalues of that critical system. That's what we did for the predator-prey equations.